Imagine you are standing at the edge of the ocean. The water stretches to the horizon in every direction. And then, for just one brief moment, maybe 5 seconds, a creature unlike anything science has ever described breaks the surface a mile offshore. It's massive. It glitters. It moves in a way that makes no sense. And then it's gone. Submerged. Racing deeper and faster than anything you own can pursue. You have binoculars. You have cameras. You have notebooks full of equations. But you have no boat fast enough. No captain ready. No fuel on the dock. And the Coast Guard is arguing about budget allocations in a committee room 3 states away. That, in the most honest and humbling terms I can offer you, is what happened to the human race in the summer of 2025. We saw it. We measured it. We photographed it. We argued about what it was. We posted about it on the internet. We wrote papers about it. Dozens of papers, hundreds of papers, an avalanche of peer-reviewed reaction. We pointed every telescope we had at it. We had spacecraft in the neighborhood, close enough that a few engineers dared to dream. And then, with the inevitable, indifferent momentum of an object that has been traveling through the darkness between stars for longer than our sun has existed, it left. It left without giving us a sample, without letting us touch it, without letting us even get close. Its name is 3I/Atlas, and I want to tell you the full story of what it is, why it matters more than perhaps anything else discovered in our lifetimes, and, most importantly, why the most technologically advanced civilization in the known history of this planet could not, in any practical sense, send a single probe to meet it. This is not a story about failure. Not exactly. It is something more uncomfortable than that. It is a story about the gap between what we know and what we can do, between our scientific imagination and our engineering reality, between the dreams we write equations for and the rockets we actually have sitting on launch pads. It is a story about speed, distance, timing, bureaucracy, physics, and the most basic fact of space travel that nobody in a movie theater ever really wants to confront. Space is not like the movies, and some visitors simply cannot be chased. Let's begin at the beginning, because every story of cosmic proportions deserves to start with a single human being, staring at a screen, about to see something that has never been seen before in the history of our species. On the morning of July 1st, 2025, a telescope in the high desert of Chile was doing what it always does: watching, scanning, cataloging, dutifully photographing patch after patch of the night sky, processing light that has traveled incomprehensible distances, and logging the results in a database that most of humanity will never read. The telescope belongs to a network called ATLAS, the Asteroid Terrestrial Impact Last Alert System. It was built to find things that might kill us, specifically rocks from our own solar system that might be on a collision course with Earth. It was not built to find messengers from another star system entirely. And yet, that is exactly what astronomer Larry Deno of the University of Hawaii found when he reviewed the data from that telescope in Chile. A faint object, a speck of light, moving fast, very fast, too fast. The kind of speed that, once you run the numbers, makes your pencil stop moving and your brain start asking uncomfortable questions. Within hours, follow-up observations began pouring in from observatories around the world. The Zwicky Transient Facility in California found pre-discovery images of the object stretching back to mid-June. Amateur astronomers dug through archival data. Professional telescopes swung to new coordinates with the urgency that only a genuinely novel discovery can produce. And within 48 hours, the Minor Planet Center, the International Clearinghouse for Solar System Object Tracking, made it official. This was a third interstellar object, designated 3I/Atlas, the third known visitor from beyond our solar system ever to be detected by human eyes and human instruments. The number 3 is important here. Tells you how rare this is. We have been watching the skies with serious scientific instruments for over a century. We have cataloged hundreds of thousands of asteroids, tens of thousands of comets, and millions of other solar system objects. We have pointed radar at rocks and bounced laser beams off the moon. We have done all of this for decades. And in all that time, in all that data, we found exactly 2 interstellar visitors before this one. The first was Oumuamua, discovered in 2017. It was peculiar in ways that still generate heated arguments at astrophysics conferences today. It showed no coma, no fuzzy cloud of gas and dust that comets typically display as they warm near the sun. Yet it accelerated non-gravitationally in ways that ice sublimation could not fully explain. It was flat, elongated, tumbling, and it arrived and departed so quickly that by the time we understood what we were looking at, it was already becoming too faint to observe. Oumuamua taught us something fundamental. The universe is willing to send us objects we cannot categorize. It was already past perihelion by the time we found it. We never had a chance to intercept it. The second was 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov from Crimea. Unlike Oumuamua, Borisov was magnificently, reassuringly comet-like. It had a coma. It outgassed. It behaved in ways our models predicted. It was, in a sense, the first interstellar object that felt familiar, a frozen traveler from another star system that happened to look a lot like the comets in our own backyard. We watched it for months. We studied it intensely, and then we watched it leave, heading back into the interstellar dark, carrying with it the secrets of whatever star system ejected it billions of years ago. But neither Oumuamua nor Borisov quite prepared the scientific community or the public for what 3I/Atlas would turn out to be. Because 3I/Atlas arrived with a particular combination of properties that made it simultaneously the most scientifically valuable interstellar object ever detected, and the most frustratingly, heartbreakingly unreachable one. Let's talk about the numbers. Because in physics, the numbers are everything. When 3I/Atlas was first spotted by the Atlas telescope in Chile, it was located between the orbits of Mars and Jupiter, roughly 4.2 astronomical units from the Sun. An astronomical unit, for those of you who prefer things in units of normal human experience, is the distance from the Earth to the Sun, about 93 million miles. So 3I/Atlas was first detected at roughly 390 million miles from the Sun, still approaching, still diving inward toward its closest encounter with our star. The speed? At the moment of discovery, approximately 137,000 miles per hour. That is not a typo. That is not a dramatic exaggeration for narrative effect. 137,000 miles per hour. For scale, our fastest bullet trains in America travel at about 220 miles per hour. The International Space Station, which we built and maintain with the combined engineering resources of 15 nations, orbits the Earth at roughly 17,500 miles per hour. The New Horizons spacecraft, which we launched in 2006 and which flew past Pluto in 2015 in one of the great achievements of human exploration, travels at approximately 36,000 miles per hour. It is currently the fastest human-made object relative to the Sun. 3I/Atlas was traveling at nearly 4 times that speed. And here is the gravitational physics that makes this fact even more dramatic. As 3I/Atlas fell toward the Sun's gravity accelerated it further. By the time it reached perihelion, its closest approach to the Sun, on October 30th, 2025, 3I/Atlas was screaming through space at approximately 153,000 miles per hour, nearly 250,000 kilometers per hour. The Sun's own gravity, that titanic 2-octillion-ton engine of force that has held our solar system together for 4.6 billion years, was used as a slingshot not by us, but by a rock from another star passing through without asking permission and without leaving a forwarding address. The eccentricity of 3I/Atlas's orbit was measured at approximately 6.1. To understand what that number means, you need to understand what eccentricity means for an orbit. A perfectly circular orbit has an eccentricity of 0. A mildly elliptical orbit like Earth's has an eccentricity of about 0.017. A very stretched, Halley-style comet orbit might have an eccentricity of 0.97. An eccentricity of exactly 1.0 is a parabola, the mathematically perfect boundary between bound and unbound. Anything above 1.0 is hyperbolic. Unbound. Escaping forever. The object is not in orbit. It is on a through trajectory. It is passing by. The eccentricity of Oumuamua was 1.2. The eccentricity of Borisov was 3.36. Both of these were dramatically, unambiguously interstellar. And yet both of those numbers are dwarfed by 3I/Atlas's eccentricity of 6.1. That is not a comet passing through. That is a freight train on rails laid before our solar system was born, aimed approximately at our sun by forces that operated in another stellar neighborhood, and now passing through ours with a velocity that carries the unmistakable signature of a journey measured in billions of years and tens of light years. When scientists traced back the trajectory of 3I/Atlas, ran the orbital mechanics in reverse, unwound the gravitational influences of the Sun and Jupiter and every other massive body in the solar system, they found that it likely originated from the galactic thick disk. This is not the thin, flat pancake of stars in which our Sun serenely orbits. The galactic thick disk is a puffier, older region of the Milky Way, populated by stars that formed 9 to 13 billion years ago, during what cosmologists poetically call cosmic noon, the period of peak star formation in the universe's history. Our own Sun is about 4.6 billion years old. The stars in the galactic thick disk are nearly 3 times older. This means 3I/Atlas may be a relic of planetary formation from a solar system that was already ancient when the Earth was still a ball of molten rock being bombarded by the last remnants of our own solar system's assembly. It may carry chemistry, mineralogy, and isotope ratios that have never existed in any material we have ever touched or sampled on Earth or from any body in our solar system. It is, in the most profound sense of the word, alien. So what does it look like? Based on observations from the Hubble Space Telescope, from the Very Large Telescope in Chile, from the Canada-France-Hawaii Telescope on Mauna Kea, from the Gemini North and South Observatories, from the Subaru Telescope, from the Webb Space Telescope, and from dozens of smaller ground-based instruments around the world, here is what we know. 3I/Atlas is a comet. It has a nucleus and a coma. That coma, the cloud of gas and dust that surrounds the nucleus as solar heat sublimes its icy surface, was clearly visible even in the earliest observations from July 2025. Unlike Oumuamua, which showed no cometary activity at all, 3I/Atlas behaved more like Borisov, an active comet outgassing volatiles, producing a measurable tail. The James Webb Space Telescope confirmed outgassing of carbon dioxide, water, and carbon monoxide. The Very Large Telescope detected cyanide gas and atomic nickel vapor. The Swift Observatory found evidence for water vapor and hydroxyl radicals. These are the signatures of a comet. A real, genuine, frozen, ice and rock comet from another solar system, now warming under the heat of our Sun for the first time in its unimaginably long journey. The nucleus, the solid body at the center of all that gas and dust, turned out to be fiendishly difficult to pin down precisely, because the coma is bright enough to overwhelm measurements of the nucleus itself. Early estimates ranged from 10 to 20 kilometers in diameter, but astronomers were quick to caution that these numbers were inflated by the coma's brightness. More careful Hubble analyses placed the nucleus diameter at a minimum of 440 meters and a maximum of about 5.6 kilometers. The most likely estimate, based on the dust ejection rate, suggested a nucleus smaller than a kilometer, which would still make it a substantial body by any reasonable measure. Something a kilometer wide, traveling at 153,000 miles per hour, is not a pebble. It is a world in miniature, with its own geology and chemistry and history. The color of 3I/Atlas was measured as reddish, a spectral slope of about 17% per 100 nanometers in the visible and near-infrared range. This redness is familiar from D-type asteroids and from Borisov. It is almost certainly caused by irradiated organic compounds called tholins, the kind of complex, tarry molecules that form when simple carbon-containing molecules are bombarded by cosmic radiation over billions of years of travel through interstellar space. In a very literal sense, the redness of 3I/Atlas is a record of its journey. Every tick of that color was laid down by cosmic rays during billions of years of travel through the interstellar medium between stars. The dust ejection rate at the time of discovery was estimated at roughly 6 kilograms per second of small dust particles and 60 kilograms per second of larger ones. For reference, that's about the mass of a compact car being shed by this comet every second. This number is comparable to Borisov's activity when it was at a similar distance from the Sun, suggesting that whatever 3I/Atlas is made of, it is subliming with approximately the vigor we might expect from a standard icy body at that heliocentric distance. And then there was the light curve, the variation in brightness over time. Early observations showed relatively little variability over a 4-day span, suggesting either that the nucleus has a relatively symmetrical shape, or that we were looking at it along an axis of rotation where brightness changes would be minimal. There were, however, 2 brief brightening events detected on consecutive nights in early July, which may represent outburst activity. Sudden jets of gas and dust from specific spots on the surface, of the kind commonly seen in solar system comets as they approach the sun, and new patches of ice reach sublimation temperatures for the first time. Now, all of this observational richness, all of these measurements, spectra, images, light curves, outgassing rates, tells you something important about the state of science in 2025. Our remote sensing capabilities are extraordinary. With the instruments we had available, we could characterize 3I/Atlas at hundreds of millions of kilometers of distance with a level of detail that would have been impossible even 20 years ago. The Webb telescope can detect the chemical signatures of molecules in a cloud of gas surrounding a rock 270 million kilometers away. That is a triumph of human engineering, mathematics, and scientific ingenuity that should not go unappreciated. But there is a question that remote sensing, no matter how sophisticated, cannot fully answer. Remote sensing can tell you what is glowing and what wavelengths are present. It can infer chemistry and temperature. It can measure velocity with extraordinary precision. What it cannot do is give you a sample. It cannot give you a close-up image of the surface geology. It cannot tell you definitively whether the isotope ratios in 3I/Atlas's water match anything in our solar system. It cannot tell you whether the organic molecules are the kind we recognize or something genuinely novel. The truly transformative science, the kind that rewrites textbooks rather than adding footnotes to existing ones, requires physical proximity. It requires a probe. And that is where the physics of this situation becomes, as one of my colleagues once put it, deeply unkind. Let's talk about what it would have taken to send a spacecraft to 3I/Atlas during its passage through the inner solar system. This is not speculation. Scientists ran the numbers. Multiple teams with different software and different assumptions converged on essentially the same conclusion. The problem has 3 components, and they interact with each other in ways that are individually painful and collectively devastating. First, speed. 3I/Atlas was moving at speeds that are fundamentally incompatible with any propulsion system currently available to humanity for a mission of this type. Think about what a spacecraft rendezvous requires. It is not enough to simply intercept the same point in space at the same time. You have to match velocities or at least come close enough to get useful observations. The ESA's Rosetta mission to Comet 67P/Churyumov-Gerasimenko took 10 years to get into orbit around its target. It launched in 2004 and arrived in 2014. And it could do that only because 67P is in a closed elliptical orbit around the Sun. It comes back. You can wait for it to be in the right place and intercept it with a manageable velocity difference. 3I/Atlas does not come back. It is on a hyperbolic trajectory. It will never return. And its velocity difference relative to any spacecraft we could launch from Earth on a direct intercept trajectory was staggering. At closest approach to Earth, December 19, 2025, at a distance of about 1.8 astronomical units, 3I/Atlas was still traveling in the opposite direction to Earth's orbit. This is the second brutal problem. 3I/Atlas was on a retrograde orbit. It was moving in the opposite direction to the planets. Earth orbits the Sun prograde, counterclockwise as seen from above the solar system's north pole, at about 30 kilometers per second. 3I/Atlas was traveling clockwise, retrograde, at speeds between 60 and 98 kilometers per second depending on when and where you measure. The relative velocity between 3I/Atlas and Earth at closest approach was not simply 60 kilometers per second. It was closer to 98 kilometers per second. To appreciate what that means for a spacecraft mission, you need to understand what velocity budget means in spaceflight. When engineers design a mission, they calculate what is called the delta V, the total change in velocity the spacecraft needs to achieve through its propulsion system. Every maneuver costs delta V. Getting off Earth costs delta V. Getting to the right orbit costs delta V. Slowing down to rendezvous costs delta V. And delta V is precious. It is the currency of spaceflight. Our best chemical rockets, the most powerful launch vehicles ever built, can provide a spacecraft with a maximum practical delta V for an interplanetary mission of somewhere in the range of 10 to 20 kilometers per second above what gravity assists can provide. To match velocities with 3I/Atlas on a direct intercept trajectory would have required a delta V of 98 kilometers per second. That is not 5 times what we can do. It is not 10 times what we can do. It is essentially impossible with any chemical propulsion system that exists or is likely to exist in the near future. Even with nuclear thermal propulsion, which has been studied extensively but never flown on an interplanetary spacecraft, the numbers remain deeply unfavorable. As Harvard astrophysicist Avi Loeb put it bluntly, our best rockets reach at most a third of the velocity difference between Earth and 3I/Atlas at closest approach. We would need an engine that does not yet exist, attached to a spacecraft that has not yet been built, launched on a mission that had not yet been planned. Third, timing. This is perhaps the most heartbreaking component of all, because it is not about technology. It is about the merciless clockwork of orbital mechanics. By the time 3I/Atlas was discovered, July 1, 2025, it was already inside the orbit of Jupiter. The window for a direct intercept mission had not just closed. It had closed weeks or months earlier, at some point when 3I/Atlas was still approaching from beyond Jupiter's orbit, still relatively accessible by spacecraft launched from Earth in a hurry. Multiple independent analyses of the trajectory data arrived at the same sobering conclusion. The optimal launch window for any direct mission to 3I/Atlas using conventional chemical propulsion had already expired before the object was even discovered. As researchers from the Initiative for Interstellar Studies put it with painful clarity, the opportunity to launch already expired before 3I/Atlas's discovery. Think about what that means for a moment. It means that there was mathematically a window that existed. There was a period, probably in early to mid-June 2025, or perhaps even earlier, when it would have been theoretically possible to launch a spacecraft on a trajectory that could have intercepted 3I/Atlas during its inner solar system transit. But during that window, we didn't know 3I/Atlas existed. The Atlas telescope wouldn't discover it until July 1st. There is a reason for this. 3I/Atlas was approaching from the direction of the galactic center, passing in front of the dense star fields of the Milky Way's central bulge, where its faint light was nearly invisible against the background. Amateur astronomer Sam Dean noted that pre-discovery observations of the object in the Atlas archive stretched back to June 5th. But even then, the object was so faint and so crowded by stellar backgrounds that routine automated detection missed it. So the universe offered us a gift wrapped in a box with no label, shipped without tracking, delivered to a mailbox we weren't checking. Now, let us talk about what we actually tried to do. Because the story of 3I/Atlas is not simply a story of helpless inaction. There was an extraordinary scramble. There were spacecraft in the neighborhood. There were creative engineers. There were brave proposals. The most immediate inventory that planetary scientists conducted was of existing spacecraft already in solar system space, probes already launched, already operating, already on trajectories that might bring them close to 3I/Atlas's path. 16 spacecraft were identified as potentially useful, and the results were educational. The Psyche spacecraft, launched in 2023 on its way to the metal-rich asteroid 16 Psyche, was calculated to pass approximately 0.302 astronomical units from 3I/Atlas on September 4, 2025, about 45 million kilometers, or the distance from Earth to Venus at close approach. That's not close in any meaningful scientific sense, but it's something. The problem: Psyche was under electric propulsion thrust during this period. Changing its trajectory to conduct useful observations of 3I/Atlas would have required temporarily shutting down its ion drive and pointing its instruments in a completely different direction, all of which introduced risk to Psyche's primary mission at 16 Psyche. Mission control and science teams had to weigh the scientific value of 3I/Atlas observations against the risk to the mission they spent billions of dollars and years of work to execute. The ESA's JUICE mission, Jupiter Icy Moons Explorer, was calculated to pass within 0.428 astronomical units of 3I/Atlas on November 4, 2025. JUICE did attempt observations in November using its JANUS camera, spectrometers, and a particle sensor. The data was extraordinary in its own right. JUICE confirmed a distinct coma around 3I/Atlas. But the spacecraft was deep in the inner solar system during a thermally challenging phase of its cruise to Jupiter, and the data couldn't even be transmitted back to Earth until February 2026. due to the demands of the spacecraft's thermal management systems. The Europa Clipper, on its way to Jupiter's moon Europa, was predicted to be immersed in 3I/Atlas's ion tail between October 30th and November 6th, 2025. This was a genuinely exciting prospect, the possibility of directly sampling the ion tail of an interstellar comet, detecting its chemical signatures with in-situ instruments rather than remote spectroscopy. The Hera spacecraft, Europe's planetary defense mission, was similarly predicted to pass through 3I/Atlas's ion tail in late October. These encounters required no special maneuvering. The spacecraft simply needed to activate their instruments as the comet's tail washed over them. And yet the closest encounter of all, the one that would have made the biggest difference, happened to the one spacecraft in the right place at what turned out to be exactly the wrong time for a different reason. The Juno spacecraft, which has been orbiting Jupiter since 2016 and has returned extraordinary science about our solar system's largest planet, would have been positioned to observe 3I/Atlas when it swung close to Jupiter in March 2026. But Juno was running low on fuel and had engine issues. Redirecting it to attempt a close encounter was not on the table. Even if the engineering had been perfect, Juno was never designed for this kind of mission, and the risk to its ongoing Jupiter observations would have been substantial. Meanwhile, researchers examined the more dramatic option. Could existing spacecraft be redirected for an actual intercept? Could we maneuver any probe into a path that would come meaningfully close to 3I/Atlas, close enough for high-resolution imaging or even the dream of dreams, some kind of in-situ measurement? The answer, arrived at through careful orbital mechanics calculations, was a sobering and essentially universal no. Commanding spacecraft to make significant trajectory changes requires large amounts of propellant, which most operational science spacecraft simply do not have. These missions were designed with specific targets and specific delta-V budgets. 3I/Atlas was not in their trajectory plans. Repurposing them for a close encounter would have been like asking a long-distance runner in the middle of a marathon to suddenly change course, run up a mountain, and still finish the race on time. And then there is the matter of what close even means for an object moving at these speeds. To conduct the kind of close flyby that would yield genuinely transformative science, close-up images of the nucleus, direct sampling of the coma, measurement of dust particle composition, you would need to be within a few thousand kilometers. At the relative velocity of 3I/Atlas to any spacecraft launched from Earth, the window of time during which a probe would be within useful observational distance of the nucleus would be measured in minutes. Hours at best. You would have minutes to do the science that took Oumuamua completely off the scientific table within weeks of its discovery and took Borisov months to characterize even with our best remote sensing telescopes. So what do we do with this? What do we learn from it? The first lesson is the one that takes a certain kind of intellectual honesty to confront. We were not ready. Not because of laziness or negligence. Not because NASA didn't care or ESA was asleep at the switch or JAXA dropped the ball. We were not ready because readiness for this kind of discovery requires something we have never had. A standing, prepositioned, rapid reaction spacecraft system capable of chasing interstellar visitors on minimal notice with sufficient delta-V to actually catch them. Nothing like that has ever been built. Nothing like that is currently being built. And as of the moment 3I/Atlas was discovered, nothing like that was even fully designed. There were proposals. There have always been proposals. After Oumuamua was discovered and lost in 2017 and 2018, a team called Project Lyra published a series of papers examining the theoretical possibility of sending a spacecraft to catch up with it. The numbers were not encouraging. Mission profiles required exotic propulsion systems, gravity assists from multiple planets, launch dates that would have required launching years before we discovered Oumuamua. Which is to say, they required knowing where to look before we had any idea where to look. After Borisov was discovered in 2019, similar analyses were conducted. Borisov was more accessible, its trajectory was prograde, its speed more manageable, but by the time the analysis was complete and any mission concept was even theoretically mature, Borisov was already departing the inner solar system. The pattern is consistent and dispiriting. We discover these objects near or past their perihelion, when they are already on their outbound trajectory. We scramble to characterize them with existing instruments. We do beautiful science at a distance, and then they leave. The problem of late discovery is partly technical and partly a matter of investment. The Atlas survey telescope that found 3I/Atlas was specifically designed and funded to detect near-Earth objects, rocks that might hit us. It was not designed with interstellar visitors in mind. And while 3I/Atlas was spotted at a relatively early stage of its inner solar system passage compared to Oumuamua, which wasn't discovered until after perihelion, relatively early still meant too late. The Vera C. Rubin Observatory in Chile, which has been ramping up operations throughout 2025 and 2026, represents a genuine quantum leap in our survey capability. With its enormous 8.4-meter mirror and its 3.2 gigapixel camera, the largest digital camera in the history of astronomy, the Rubin Observatory is expected to detect roughly one new interstellar object per year. One per year, compared to the 3 we found in the previous 8 years using all our previous instruments combined. This is genuinely transformative. With earlier detection, potentially months or even years before perihelion, the mission calculus changes dramatically. But detection is only one component of the problem. The other is the standing question of what you do when you find one. Because the time between discovery and launch for any serious spacecraft mission has historically been measured not in weeks or months, but in years or decades. The Parker Solar Probe, which now holds the record for the closest approach to the Sun by any human-made object, was first proposed in the 1950s and launched in 2018. New Horizons was proposed in the 1990s and launched in 2006. The James Webb Space Telescope was first proposed in 1996 and launched in 2021. These timescales are not aberrations. They are features of the scientific, engineering, political, and budgetary process by which humanity builds and operates spacecraft. To catch an interstellar visitor requires a fundamentally different approach. It requires having a spacecraft or the components of one, already in a state of advanced readiness, capable of being launched on notice measured in days or weeks rather than years or decades. This is not a new idea. It has been discussed in the scientific community with increasing seriousness since Oumuamua. The European Space Agency has conducted internal studies on interstellar object interceptor mission concepts. NASA has had workshops. Private organizations like the Initiative for Interstellar Studies have published papers. The ingredients of a solution are understood in broad outline. A pre-built spacecraft on standby, with a sufficiently large propulsion system to enable rapid trajectory changes, kept in some accessible storage configuration until an interstellar object of sufficient interest is detected. The challenge, as always with space exploration, is not conceptual. It is political, financial, and institutional. A spacecraft on standby is a spacecraft that costs money without producing science. In a budget environment where missions compete for funding, where congressional appropriations are subject to political winds that shift every election cycle, and where the long timescales of space missions make short-term ROI essentially impossible to demonstrate, a readiness-focused mission without a specific target is extraordinarily difficult to fund. And so we found ourselves, in the summer and fall of 2025, doing the best we could with what we had, which was spectacular telescopes, brilliant scientists, existing spacecraft that were not designed for this purpose, and absolutely no hardware ready to launch. Let's talk about what the scientists did manage to accomplish, because it is genuinely impressive. The campaign of observations conducted during 3I/Atlas's passage through the inner solar system represents one of the most intensive and coordinated observational efforts in the history of astronomy. Every major ground-based telescope on Earth was pointed at it at some point. The Hubble Space Telescope watched it from Earth orbit, free of atmospheric blurring. The James Webb Space Telescope characterized its chemical composition. The SphereX mission, a NASA survey telescope that had recently launched, detected organic molecules in its coma. The Very Large Telescope in Chile measured its rotation period and obtained spectra of its surface and coma. The rotation period, derived from painstaking photometric monitoring, was determined to be approximately 16.79 hours. This gives us information about the object's shape, its internal structure, and the distribution of mass within the nucleus. The non-gravitational acceleration, the extra push beyond what gravity alone would predict, caused by jets of outgassing material acting like tiny rocket engines, was measured with precision as the comet rounded the Sun. At its peak, This non-gravitational acceleration reached a value of approximately 89.3 plus or minus 4.6 times 10 to the negative ninth power astronomical units per day squared, measured 1 month before perihelion. That number is significant. Non-gravitational acceleration is the fingerprint of cometary activity. It tells you about the intensity of outgassing, the distribution of active regions on the surface, and the volatile budget of the nucleus. For 3I/Atlas, these measurements implied substantial activity, consistent with a comet that has a meaningful inventory of water ice, carbon dioxide ice, and other volatiles that are being baked off by solar heat for what may be the very first time. The fact that it is almost certainly the first time this ice has ever experienced solar heat at this proximity is a thought that should give you pause. Every molecule of water vapor in 3I/Atlas's coma was ice in another solar system, ice that formed around another star, that was ejected into interstellar space, that traveled across tens of light years and billions of years, and then was warmed by our sun for the first time. The steam that clouds its coma is the first interaction of that ancient ice with our stellar neighborhood. There was also the matter of the trajectory itself, its geometry, which became one of the most debated aspects of 3I/Atlas's passage. The orbit of 3I/Atlas was retrograde, going the wrong way around the sun compared to the planets. That alone is unusual but not unprecedented among solar system comets. What made it remarkable was the inclination, 175 degrees. This means 3I/Atlas was moving in the opposite direction to Earth's orbit, but its orbital plane was almost exactly aligned with the ecliptic, the flat plane in which the planets orbit. The tilt away from the ecliptic plane was only about 5 degrees. This geometric alignment had two immediate consequences. The first was scientific. It meant that 3I/Atlas's trajectory brought it unusually close to multiple planets. During its transit of the inner solar system, 3I/Atlas passed close to Venus, Mars, and Jupiter in sequence, not Earth, but 3 of the 4 other inner solar system bodies. The probability of a randomly directed interstellar object making close passes to Venus, Mars, and Jupiter in a single transit has been estimated at roughly 1 in 20,000. It is a remarkable geometric coincidence, or, as some researchers with more dramatic imaginations suggested, possibly something more than coincidence. This brings us to the part of the 3I/Atlas story that is important to address with both honesty and appropriate skepticism, because it attracted an extraordinary amount of public attention and generated more heat than light in many online discussions. Harvard astrophysicist Avi Loeb, who is a brilliant scientist with a genuine and important track record in astrophysics, and who is also known for being willing to propose hypotheses that his colleagues find premature, made a series of public claims about 3I/Atlas that captured the imagination of the internet. Specifically, Loeb suggested that 3I/Atlas might not be a natural comet at all. He pointed to what he characterized as anomalous characteristics: the improbable alignment with the ecliptic plane, the close passes to multiple planets, the retrograde motion that he argued would make it particularly difficult for humans to intercept while being relatively easy for a technologically sophisticated object to use for planetary reconnaissance. He speculated, in papers posted to scientific preprint servers on his blog, and in numerous media appearances, that 3I/Atlas could be an extraterrestrial spacecraft. A mothership in some of the more colorful formulations. The scientific community responded with polite but firm disagreement. Daryl Seligman, who led the first major peer-reviewed paper on 3I/Atlas, was characteristically direct. The object was displaying classical signatures of cometary activity. It was outgassing. It had a coma. The James Webb Space Telescope detected water, carbon dioxide, and carbon monoxide, all entirely standard for comets. The Very Large Telescope detected cyanide and nickel, also found in solar system comets. The spectral color was consistent with irradiated organics, tholins, the same kinds of molecules found on D-type asteroids and on Borisov. Each anomaly that Loeb listed had a natural explanation, and the collective judgment of the planetary science community was that 3I/Atlas was an extraordinary object, but an extraordinary natural object. The ecliptic alignment, while statistically unusual, is not impossible. 1 in 500 objects would show such alignment by pure chance, and given the number of interstellar objects that have probably passed through our solar system over its history, such an alignment was bound to happen eventually. The close passes to Venus, Mars, and Jupiter, while genuinely striking, reflect a trajectory that is, after all, constrained by having passed close to the Sun at $1.35. Given that geometry, the gravitational dynamics of the inner solar system made such planet encounters more likely, not less. What this debate illustrates, more than any scientific conclusion about 3I/Atlas itself, is the profound and legitimate scientific hunger for direct data. If we had a sample of 3I/Atlas, even a microscopic grain of its surface material, the alien spacecraft hypothesis would be testable in laboratory rather than argued about in papers. Chemistry doesn't lie. Isotope ratios don't lie. Crystal structures don't lie. If you have a sample, we do not have a sample. We may never have a sample. And this is perhaps the deepest wound left by humanity's failure to intercept 3I/Atlas. Not the data we lost, but the certainty we were denied. Now let us look forward. Because the story of 3I/Atlas is not over, and the story of humanity's relationship with interstellar visitors is, if we are wise, only at its very beginning. First, the near-term situation with 3I/Atlas itself. The comet continues its outbound journey, receding from the Sun at approximately 61 kilometers per second. By March 2026, it swings through the vicinity of Jupiter, offering Juno its last possible observational opportunity. After that, it crosses the outer solar system and heads back into the interstellar dark from which it came. It will never return. In 10 years, it will be beyond the orbit of Pluto. In 100 years, it will be in the space between stars. In 1,000 years, it will be further from our Sun than any human-made object has ever traveled. There is, however, a mission proposal on the table. It is ambitious to a degree that requires the word ambitious to work harder than it usually does. And it is proposed not for the near future, but for a decade from now. The proposal comes from Adam Hibbard of the Initiative for Interstellar Studies and T. Marshall Eubanks of Space Initiatives Incorporated. Their paper, published in early 2026, proposes what is called a solar Oberth maneuver mission to 3I/Atlas, with an optimal launch date of 2035. The solar Oberth maneuver is one of those ideas that, when you first encounter it, sounds like science fiction, and then, when you work through the mathematics, becomes a kind of poetry of physics. Here is the concept. Hermann Oberth was an Austro-Hungarian rocket scientist who, in 1929, formalized a principle that now bears his name, the Oberth effect. The essence of the effect is this: the energy gained by firing a rocket engine depends not just on how much fuel you burn, but on how fast you are moving when you burn it. The faster you are moving when your engines fire, the more kinetic energy you gain from the same amount of propellant. This is counterintuitive if you think about rockets the way you think about cars, as machines that simply add speed. But rockets don't just add speed. They add momentum, and momentum times velocity equals kinetic energy, which means burning fuel at high velocity gives you dramatically more energy than burning the same fuel at low velocity. The implication for deep space missions is profound and somewhat paradoxical. The most efficient place to fire a rocket is as close as possible to the most massive gravitational body available, because that is where the spacecraft is moving fastest. The Sun is the most massive body in our solar system. A spacecraft that falls close to the Sun, very close within a few solar radii of its surface, achieves velocities that dwarf anything achievable in the outer solar system. And if you fire your engines at that moment of maximum speed, the energy boost is incomparably greater than anything achievable further out. This is not just theoretical. The Parker Solar Probe has demonstrated that a spacecraft with sufficient thermal protection can survive extremely close solar approaches. Parker has approached to within about 9 solar radii of the Sun's surface and survived temperatures of 1,370 degrees Celsius, thanks to its sophisticated carbon composite heat shield. The Hibbard-Eubanks mission proposal would take this concept further, approaching to within 3.2 solar radii. The mission profile works like this. Launch from Earth in 2035. Fly to Jupiter, a journey of about 1 year. At Jupiter, use the giant planet's gravity for a braking maneuver. Paradoxically, you slow down at Jupiter in order to fall deeper into the Sun's gravity well. Then fall toward the Sun. As the spacecraft nears its closest solar approach at 3.2 solar radii, roughly 2.2 million kilometers from the solar surface, where temperatures approach 1,400 degrees Celsius, fire all available engines in one intense, carefully timed burst. This is the Oberth burn. All the fuel in one moment at the moment of maximum speed. The spacecraft then rockets outward from the Sun at a velocity that would make it the fastest human-made object ever built. Faster than Voyager 1, faster than New Horizons, faster than anything that has ever left this planet's gravity. Fast enough, perhaps, to catch up with 3I/Atlas eventually. Eventually. In this context, that word means 35 to 50 years. Even with a solar Oberth maneuver, even launched in 2035, the proposed spacecraft would not intercept 3I/Atlas until somewhere between 2070 and 2085, at a distance of roughly 732 astronomical units from the Sun, about 68 billion miles. For reference, Voyager 1, launched in 1977 and now the most distant human-made object, has traveled about 165 astronomical units in 48 years. This mission would reach 4 times that distance in roughly the same time. The proposed spacecraft would have a mass of roughly 500 kilograms, comparable to the New Horizons probe that gave us our first close-up images of Pluto. A significant portion of that mass budget would be devoted to thermal protection for the solar approach, a multi-layer carbon composite heat shield with aerogel insulation, similar in concept to Parker solar probes but pushed to even more extreme conditions. The propulsion for the Oberth burn itself would be provided by multiple solid rocket boosters, with the entire assembly launched from Earth aboard a SpaceX Starship Block 3 refueled in low Earth orbit. This last requirement, Starship Block 3 with in-orbit refueling, is not a currently available capability. Orbital refueling of Starship has been demonstrated in early form, but the Block 3 variant and the operational cadence required for this kind of mission represent technology that is still in development. This is not a showstopper, it is a requirement that is plausibly achievable by 2035, but it illustrates that even this feasible mission proposal requires pushing the envelope of what currently exists. And even then, the scientific outcome of the mission is a flyby. One brief, fast encounter with 3I/Atlas, at a closing velocity that would allow only minutes of close observation. High-resolution imaging of the nucleus. In situ dust sampling if appropriate instruments are included. Chemical analysis of the coma. All of this conducted at planetary distances from our solar system, with a communication time lag that at 732 Australian dollars would be measured in days. About 5 days at the speed of light each way for a round-trip data transmission. Is it worth it? This is a question that seems almost absurdly modest when you stop and actually think about what 3I/Atlas is. It is a piece of another solar system. It is a fragment of planetary formation from 9 to 13 billion years ago. It carries chemistry that has never existed in any material available to us. Even a brief flyby encounter, even minutes of close-up data at enormous distance, would represent the first direct scientific contact with the material of another solar system. It would answer questions about whether the chemistry of planetary formation is universal or parochial. It would test whether the building blocks of life that we find in our solar system are common or rare. It would tell us things about the evolution of galaxies, of stellar populations, of the history of the universe that we cannot learn from anything available in our own solar system. Yes, it is worth it. It has always been worth it. But here is the most important forward-looking implication of the 3I/Atlas story, and it is one that scientists and science policy experts have been arguing for forcefully in the wake of 3I/Atlas's discovery and departure. We need to be ready for the next one. The Vera C. Rubin Observatory changes the detection calculus fundamentally. With the Large Synoptic Survey Telescope at its heart, Rubin can survey the entire visible southern sky every few nights, detecting objects orders of magnitude fainter than what Atlas can find. Simulations suggest that Rubin will find roughly 1 interstellar object per year, potentially detecting them months or even years before perihelion, when they are still in the outer solar system on their inbound trajectory. This earlier detection window is transformative for mission planning. An object detected at 5 or 6 Australian dollars from the Sun, with months of advance notice, opens mission windows that are simply impossible when detection happens inside Jupiter's orbit. But Rubin detection is only part of the answer. The other part requires something that is politically and institutionally difficult: pre-built, standing-ready mission hardware. The concept that has been discussed most seriously is sometimes called an interstellar object interceptor, a spacecraft kept in a state of high readiness, possibly in low Earth orbit or at a Lagrange point, capable of being directed at a newly discovered interstellar visitor with a launch notice measured in weeks rather than years. This is an expensive proposition. Keeping a spacecraft in standby is not cheap. The instruments must be maintained. The propulsion system must be ready. The mission operations team must exist and be funded. And all of this must be sustained indefinitely with no specific target and no defined mission end date, waiting for an opportunity that might come next year or might come in 30 years. The scientific case for this investment has rarely been stronger. 3I/Atlas has demonstrated with crystalline clarity what is at stake. The questions that cannot be answered by remote sensing, questions about isotope ratios, about organic chemistry, about mineralogy, about the deep history of another stellar system, can only be answered by physical proximity. And physical proximity to interstellar visitors requires readiness that we do not currently possess. There is also the question of what we learn about our own solar system by studying interstellar visitors. The current best estimate of the flux of interstellar objects passing through our solar system, based on the detection rate from ATLAS and earlier surveys, suggests that at any given moment, there are probably hundreds of interstellar objects of the size of 3I/Atlas within the inner solar system, passing through undetected or undetectable with current instruments. The interstellar medium is, in some sense, not the empty void we sometimes imagine it to be. It is filled with the debris of planetary systems, the ejecta of billions of years of collisions, gravitational encounters, stellar flybys, and disk instabilities playing out across every star system in the galaxy. We are swimming in a sea of other people's rocks. Every one of those rocks carries information. Every one is a sample return mission that the universe has already paid for in terms of delta V. It has accelerated these objects to interstellar velocities and delivered them to our solar system, free of charge. All we have to do is reach out and take one. And we have not yet done that. Not once. Not ever. The closest any human artifact has come to interstellar material is the Stardust mission's collection of particles from Comet Wild 2. Material that was almost certainly from the outer solar system and may have contained some pristine interstellar grains. The Genesis mission collected solar wind particles. The Hayabusa and Hayabusa 2 missions returned samples from asteroids. But none of these missions touched material that originated outside our solar system in any definitive sense. Our sample collection capability, for all its achievement, has been limited to our own cosmic neighborhood. 3I/Atlas flew through that neighborhood at 153,000 miles per hour and we watched it go. There is a certain kind of person who responds to a situation like this with frustration directed at the institutions involved. Why didn't NASA act faster? Why didn't ESA mount an emergency mission? Why isn't there already a readiness spacecraft sitting in Earth orbit? These are fair questions, and they deserve serious answers rather than bureaucratic deflection. The honest answer is that the scientific community has known, in principle, that interstellar objects would eventually be discovered. Oumuamua proved it in 2017, and the response to that knowledge has been inadequate. The workshop reports and mission concept studies and white papers have multiplied. The funding for actual hardware has not materialized at the scale required. This is not a failure of scientific imagination. It is a failure of institutional priority setting and political will. In a space program that spends billions on missions to destinations within our solar system, a dedicated interstellar object interceptor mission has consistently been judged as less urgent than the next planetary mission, the next telescope, the next instrument. 3I/Atlas has, one can hope, changed that calculus. The scale of the lost opportunity is now tangible in a way that no amount of theoretical argument about interstellar object detection rates could make it. We didn't just miss detecting an interstellar visitor. We detected one, watched it for months, photographed it with the greatest telescopes ever built, and then watched it leave, carrying the answers to questions we cannot answer from here. That is a specific, documented, measurable failure of preparation. And it is the kind of failure that, if it happens again, will be much harder to explain away. So what is the right ending for this story? Because the best documentaries, the ones that deserve their place on the screens of curious people who want to understand the universe, don't just describe what happened. They help you understand what it means. What it means is this: we live at an extraordinary moment in the history of both science and civilization. We have instruments that can detect a rock the size of a stadium at 400 million miles away, characterize its chemistry, measure its spin, and determine that it came from a solar system that was old when our sun was young. That is a genuinely staggering capability. It represents centuries of accumulated human ingenuity, mathematics, engineering, international cooperation, and institutional investment. The fact that we can watch 3I/Atlas at all is a triumph. But the capability to observe is not the same as the capability to explore. And the history of science is fundamentally a history of the difference between watching and touching. We watched the moon for millennia before we landed on it. We watched Mars for centuries before we rolled a rover across its surface. We watched comets for millennia before we flew through one's coma, landed a probe on one, and returned samples from another. The next step in our relationship with interstellar material is not to watch more interstellar objects go by. It is to go get one, to catch up with a visitor from another solar system and bring back a piece of it, or at the very least, fly close enough to look it in the face. The technology is not far beyond our current capability. The Solar Oberth Maneuver mission proposed for 2035 is not science fiction. It is engineering that requires pushing existing technologies, not inventing new ones. The Rubin Observatory, now operational, will find us more targets. The SpaceX Starship, for all the turbulence of its development program, represents the most powerful launch vehicle in history and the plausible enabler of mission mass budgets that were previously impossible. Nuclear thermal propulsion, which would dramatically reduce the transit times involved in these missions, has been studied for decades and is closer to flight qualification than at any previous point in history. The ingredients are present. The scientific motivation has never been clearer. The cost of inaction has been demonstrated with painful specificity by 3I/Atlas. What remains is the hardest ingredient of all: the sustained human attention span required to fund, build, launch, and operate a mission with a 10-year development timeline, a decades-long cruise, and a scientific payoff that will be collected by people who have not yet been born. This is what space exploration has always asked of us. It is what Kennedy asked of us in 1961 when he announced a moon landing within the decade, when no American had yet been to orbit, when the rockets required didn't yet exist, when the engineering challenges were barely articulated. It is what the designers of Voyager asked of us when they sent those twin probes outward in 1977 with the expectation that they would still be returning data in the 21st century. It is what the engineers of New Horizons asked when they proposed in the 1990s to fly past a world at the edge of the solar system that most people had never heard of. These missions succeeded not because the technology was easy, but because enough people decided that the destination was worth the difficulty. 3I/Atlas has told us, with the eloquence that only physics can produce, that there are destinations beyond our solar system that are worth the difficulty. Objects from other stellar systems, carrying the chemistry of other planetary histories, occasionally drift through our neighborhood. They give us brief windows of opportunity, months, not years. And to take advantage of those windows requires a level of preparation that we have not yet achieved. The most important thing 3I/Atlas has given us is not data. It has given us clarity. Clarity about what we are capable of observing and what we are still incapable of reaching. Clarity about the gap between our scientific ambitions and our engineering readiness. Clarity about the cost of not being prepared. Clarity about what the universe is willing to offer us, if we are willing to rise to meet it. 3I/Atlas is, as of today, somewhere beyond the orbit of Jupiter, decelerating under the sun's diminishing gravity, heading back into the interstellar dark at 61 kilometers per second. It will be beyond Pluto's orbit in roughly a decade. Beyond the heliopause, the outer boundary of our sun's influence, in perhaps 2 to 3 decades. And then it will be in the vast, empty, ancient silence between the stars again, carrying its information back into the darkness, as it has been doing for perhaps 10 billion years before it even passed through our neighborhood. It does not know we exist. It does not care that we watched it. It does not feel the weight of the opportunity it represented or the frustration of its passing. It is a rock, however extraordinary a rock it may be. The significance, the meaning, the urgency, the lesson exists entirely on our side of this encounter. And the lesson is this: the universe has been sending us visitors from beyond our solar system for as long as our solar system has existed. One day, perhaps soon, perhaps in the next few years, with Rubin watching the sky, we will discover another one. And when we do, the question we will face is the same one we faced in July 2025 and failed to answer. Are we ready? As of July 2025, the answer was no. The question of whether it will be different next time is not a question about physics or engineering. It is a question about who we decide to be, about whether we choose to be a species that watches the universe go by, or one that reaches out and touches it. I know which choice I would make, and I think if you've made it this far, I know which one you would make too. The stars have been sending us messages for a long time. 3I/Atlas was the third in recorded history. Somewhere out there, perhaps already crossing the outer solar system, perhaps still years away, the fourth is approaching. The question is whether, when it arrives, we will still be standing on the shore watching the ripples it leaves behind, or whether we will finally have a boat. Let me take a step back and put all of this in a context that I think is sometimes missing from the breathless coverage that interstellar objects tend to generate. Because when a Harvard professor starts talking about alien motherships and the internet catches fire and half the YouTube algorithm redirects itself toward glowing orb footage, it can become easy to lose track of something more fundamental. Something that, to a scientist or an engineer, is actually more astonishing than the alien hypothesis. More humbling, more demanding of reflection. We are talking about rocks. Magnificent, ancient, chemically complex, scientifically irreplaceable rocks from another solar system. But rocks, objects that were formed by the same physical processes. Gravity collapsing a cloud of gas and dust, heat and pressure fusing that dust into larger bodies, collisions breaking some of those bodies apart and scattering the fragments that formed every asteroid, comet, moon, and planet in our own solar system. The same laws of physics that govern our local cosmic neighborhood govern the cosmos at every scale we have ever been able to measure. And that universality means that a chunk of a planetary disk from 9 billion years ago, in a solar system in the galactic thick disk, is made of atoms that obey the same quantum mechanical rules as the atoms in the chair you're sitting on right now. What makes 3I/Atlas precious is not its alienness in the sense of being incomprehensibly different. What makes it precious is its specificity, the fact that it carries the particular history of a particular place and time in cosmic history that we cannot access any other way. The thick disk stars are old, metal-poor. Their planetary systems, if they had them, formed from material with a different abundance of heavy elements than the solar nebula from which our sun and planets formed. The ratio of carbon to oxygen in those systems, the abundance of sulfur relative to silicon, the presence or absence of certain isotopes of magnesium and iron and nickel. All of these ratios carry the fingerprints of nucleosynthesis in stars that lived and died billions of years before our sun was born. These are the questions that cosmochemists dream about. The people who spend their careers analyzing the tiniest grains inside the most primitive meteorites, chondritic meteorites, the ancient, barely processed fragments of our own solar system's formation. These are the questions that drive them. What was the early solar system made of? How did those ingredients vary from place to place? How does the chemistry of planetary formation differ between old star systems and young ones, between metal-rich systems and metal-poor ones, between the galactic thin disk and the thick disk? To answer those questions today, we work backward from the solar system's current inventory: meteorites, comets, asteroids, the compositions of planetary atmospheres. We compare these measurements to what we see in other star systems, the spectral signatures of protoplanetary disks, the compositions of exoplanet atmospheres where we can measure them, the abundances in stellar spectra. It is painstaking work, done with extraordinary precision, but it is always indirect, always inferential, always constrained by the fact that we are measuring the end products of billions of years of processing and trying to reconstruct the initial conditions from those end products. A sample of 3I/Atlas would have been different. It would have been a direct sample of the building material of a planetary system from a different era and a different place in the galaxy. Not inferred, not modeled, measured, in a laboratory, with instruments that can determine isotope ratios to parts per million and identify organic molecules by their specific molecular structure. The kind of data that ends arguments rather than spawning new ones. This is why the failure to intercept 3I/Atlas stings with a particular sharpness for scientists who have spent decades thinking about these questions. It is not the loss of an interesting data point. It is the loss of a transformative dataset, the kind that changes the paradigm rather than refining the existing one. And it is worth asking, honestly and without defensiveness, Could we have been better positioned? The answer requires separating two distinct time horizons. In the very short term, the weeks and months after 3I/Atlas was discovered, there was very little that could have been done differently. The launch window had already closed by the time the object was identified. No amount of rapid response could have changed the fundamental orbital mechanics. The spacecraft that were in the neighborhood were not designed for this purpose, and redirecting them posed risks to their primary missions. This was a genuine case where the constraint was physics, not bureaucracy. But in the medium term, the years since Oumuamua's discovery in 2017, the story is more complicated. Because Oumuamua taught us with perfect clarity that interstellar objects exist and that they pass through our solar system. It taught us that when they do, the discovery window is short and the mission window is shorter. It gave us 8 years, from 2017 to 2025, to prepare for the next one. And during those 8 years, we built no interceptor. We funded no standby mission. We made progress on telescope surveys and we wrote many thoughtful papers, but we did not build hardware. This is not a criticism that applies to any single institution or individual. It is a structural observation about how space agencies allocate resources and how the political system that funds them operates. Long-horizon investments with uncertain timelines and diffuse scientific benefits are chronically underfunded relative to near-term, well-defined missions with specific targets and predictable outcomes. A moon return mission has a destination. A Mars landing has a destination. A flyby of an interstellar object has no destination, it has a category. And categories are much harder to fund than destinations. The 3I/Atlas episode has, however, created a political and scientific moment that advocates for an interceptor mission are right to try to exploit. The images of 3I/Atlas are striking and widely shared. The public engagement with the story, even the alien mothership discourse, frustrating as it is to scientists, demonstrates that there is genuine popular interest in interstellar objects. And popular interest, properly channeled, is one of the most powerful drivers of space program funding. Apollo was popular partly because the Cold War made it urgent and partly because it captured the imagination of an entire generation. The moon landing was watched by an estimated 600 million people. Pluto flyby images from New Horizons were downloaded 40 million times in the first month after the encounter. Public engagement matters. It translates into congressional support, which translates into funding, which translates into hardware. The story of 3I/Atlas needs to be told in a way that captures both its scientific profundity and its practical lesson. Not just as a wonder, though it is a wonder, but as a call to action. A demonstration of what is possible to see and what remains, for now, beyond our reach. An argument written in the language of orbital mechanics and human frustration for why we need to be better prepared. Now let's dwell for a moment on the sheer otherness of what 3I/Atlas is, not in a mystical sense, but in a physical, geological, chemical sense that I think gets lost in the abstraction of astronomical measurements. Picture a comet in our own solar system. Take Halley's Comet, perhaps the most famous comet in human history. Halley is a body about 15 by 8 kilometers, shaped somewhat like a peanut, tumbling through an elongated ellipse that brings it within the inner solar system every 75 years or so. Its surface is darker than coal, one of the darkest surfaces in the solar system, covered with a thin crust of organic material beneath which lie ices. Water ice, carbon dioxide ice, carbon monoxide ice. When Halley approaches the sun, the thin dark crust heats up unevenly, and the ices beneath it sublimate through cracks and weak spots, creating jets that push material into space in a fountain of gas and dust. That material forms the coma and the tail. That is a comet. That is the process that 3I/Atlas is replicating, albeit with material from a different place and a different time. But the key difference is the history embedded in Halley's material. Halley formed in our own protoplanetary disk, from the same molecular cloud that formed the Sun and all the other planets. Its chemistry, while primitive and ancient, reflects the specific abundances of elements in our solar system's birthplace. A specific molecular cloud in the Milky Way, roughly 4.6 billion years ago, at a specific location in the thin disk of the galaxy. Every comet in our solar system shares this heritage. Every asteroid, every planet, they all drank from the same original well. 3I/Atlas did not drink from that well. Its heritage is entirely different. The molecular cloud that formed its parent stellar system was in the galactic thick disk, an older, puffier, more turbulent region of the Milky Way, populated by stars that formed when the universe was young and metal-poor and star formation was proceeding at a furious pace. The material in that molecular cloud had been processed differently, through a different history of supernovae, through different rates of nucleosynthesis, through different abundances of neutron capture elements. The R process and S process nucleosynthesis that build the heavy elements in stars, the gold, the platinum, the uranium, the lead, proceeded at different rates and proportions in that environment compared to the one that formed our sun. All of that history is encoded in 3I/Atlas's atomic structure, in the ratios of its isotopes, in the crystal structures of its silicate minerals, in the specific organic molecules present in its coma. And none of that information can be read from a distance with a spectrograph, no matter how sensitive. You need the material itself. You need to hold it in a laboratory, dissolve it in acid, separate its elements in a mass spectrometer, and read the isotopic fingerprints that 10 billion years of cosmic history have written into its atoms. The scientists who study meteorites, people like cosmogeochemist Gary Huss or Caroline Smith at the Natural History Museum in London, will tell you that even a microgram of 3I/Atlas material would be among the most scientifically valuable substances ever collected. More valuable in terms of information content per gram than lunar samples. More valuable than the Ryugu asteroid samples returned by Hayabusa 2. Because while those samples are extraordinary in their own right, they are fundamentally samples of our own solar system. 3I/Atlas material would be something else entirely. A sample from another cosmic address. Let me also address the question of scale, both spatial and temporal, in a way that I think is genuinely difficult to internalize even for people who work with these numbers every day. 3I/Atlas, before it arrived in our solar system, had been traveling through interstellar space for a very long time. How long? The galactic thick disk, from which it likely originated, contains stars that formed between 9 and 13 billion years ago. If 3I/Atlas formed in a planetary system around one of those ancient stars, it was ejected into interstellar space at some point, perhaps during a gravitational encounter between forming planets, or as a result of a stellar flyby, or when its parent star evolved off the main sequence and its planetary system was disrupted. Let's say it was ejected even a billion years after its formation, so perhaps 8 to 12 billion years ago. In all that time, traveling at roughly 60 kilometers per second through interstellar space, the speed it would have had after the gravitational dynamics of its ejection and the subsequent motion of the galactic thick disk 3I/Atlas would have traveled an extraordinary distance. At 60 kilometers per second, in 1 billion years, it covers roughly 60 light-years. In 10 billion years, roughly 600 light-years. The galaxy is about 100,000 light-years across and 1,000 light-years thick in the vicinity of our Sun. In 10 billion years, 3I/Atlas could have crossed the galactic disk many times, visited the neighborhoods of thousands of stars, and ultimately arrived at ours by a combination of its own ancient momentum and the gradual drift of stellar populations through the galaxy. It arrived at our solar system having never before been within the illuminating warmth of a star, or if it was, it has been cold for so long that any memory of prior stellar warmth has been overwritten by the cosmic radiation processing that gives it its red color and by the steady evolution of its surface chemistry over billions of years in the ultraviolet and particle radiation of the interstellar medium. The water that makes up part of its ice. The water that the James Webb Space Telescope detected sublimating into its coma as it warmed under our sun. That water was formed when the universe was young. Those hydrogen atoms and oxygen atoms were assembled into water molecules in the molecular cloud of another star system, billions of years before Earth existed. They were incorporated into a planetesimal, frozen solid. They drifted through interstellar space. And then, in October 2025, as 3I/Atlas passed its closest approach to our Sun at 1.35 astronomical units, roughly the distance of Mars from the Sun, that ancient water ice sublimated for the first time, perhaps for the first time since the cosmos was young. The steam that rose from its surface as it rounded the sun was water vapor that had never touched sunlight before. If that doesn't make you feel something, some combination of wonder and inadequacy and urgency, I'm not sure what kind of cosmic event would do the job. And we watched it through telescopes. I want to spend a moment on the human dimension of this, on the scientists who dedicated months of their professional lives to studying 3I/Atlas, who wrote dozens of papers in the months after its discovery, who argued and debated and measured and published at a pace that the academic publishing system barely had the infrastructure to accommodate. Because this story is not just about the failure to send a probe. It is also about an extraordinary scientific response to a once-in-a-generation opportunity. Consider what happened in the weeks after discovery. Within 48 hours of the July 1st announcement, observatories on every continent were generating data. Within a week, the first peer-reviewed analyses were being posted to AR14, the scientific preprint server where physicists and astronomers share their work before formal publication. Within a month, there were dozens of papers on the orbital mechanics, on the spectral properties, on the coma morphology, on the dust ejection rates, on the non-gravitational accelerations, on the mission design challenges, on the galactic origin inference, on the comparison with Borisov and Oumuamua. The pace of publication was extraordinary even by the standards of fast-moving modern science. Scientists who had data from a given night's telescope observations were often posting analysis within days. This speed was partly enabled by the infrastructure of modern astronomy, digital detectors, automated pipelines, AR14, global email networks, and partly a reflection of the genuine urgency that every astronomer working on 3I/Atlas felt. They knew the window was limited. They knew that in a matter of weeks, the comet would pass behind the sun and be unobservable from Earth for weeks. They knew that after perihelion, it would be heading away from the sun and its activity would diminish. Every observation had value. Every night of clear weather at a major telescope was a night that could add to the scientific record of this unique visitor. The global coordination was also remarkable. Telescopes in Chile, Hawaii, Arizona, New Mexico, the Canary Islands, South Africa, Australia, and India all contributed observations. The Hubble Space Telescope was pointed at it repeatedly. The James Webb Space Telescope interrupted its scheduled program to observe it, a decision that requires formal approval and represents a significant commitment of the most expensive and in-demand scientific instrument in human history. The JUICE spacecraft, on its way to Jupiter, not designed for comet observations, thermally stressed by its transit through the inner solar system, activated its instruments and made observations that were the most distant in situ measurements of 3I/Atlas ever made. This is science working the way it should work. Rapidly, cooperatively, transparently, with data shared quickly and openly across international boundaries and institutional affiliations. The scientific response to 3I/Atlas was, in many respects, a success. We learned an enormous amount in a very short time. The cumulative scientific output from the 3I/Atlas observation campaign represents a genuine advance in our understanding of interstellar objects, of cometary science, of the galactic disk populations that might be producing these visitors. But the success of the observational campaign makes the absence of a probe even more poignant. Imagine a scenario in which, instead of, or in addition to, all those telescope observations, there had been a spacecraft in the coma of 3I/Atlas, imaging the nucleus at 10-meter resolution, collecting dust particles with ion traps, measuring the magnetic field, analyzing the composition of the gas directly with mass spectrometers rather than inferred from spectral lines measured at millions of kilometers of distance. The data returned from such a mission would have been transformative, not in the marginal sense that most science advances are transformative, adding to what we know, but in the fundamental sense, it would have shown us something genuinely new about how the universe works. Instead, we have beautifully done remote sensing, which is extraordinary and insufficient. One more thing deserves attention, and it is the thing that tends to get lost when discussions of 3I/Atlas migrate from the science pages to the entertainment pages. The alien hypothesis. Avi Loeb is not a fringe figure. He is a serious astrophysicist with a long and genuinely distinguished publication record in fields ranging from the early universe to black holes to the formation of the first stars. He has written important papers on topics that have nothing to do with extraterrestrial intelligence. He is also a person who has, in recent years, staked a significant portion of his public reputation on the proposition that we should take seriously the possibility that some anomalous astronomical objects might be of technological origin, not as a certainty, not as a likelihood, but as a scientific hypothesis that deserves to be tested rather than dismissed by assumption. This is a defensible philosophical position. Science advances by testing hypotheses, not by declaring them untestable. And the question of whether technological civilizations exist elsewhere in the universe is one of the most profound questions in all of science, one that we have no definitive answer to. But the hypothesis requires evidence proportional to its claim. And in the case of 3I/Atlas, the anomalies that Loeb cited, the ecliptic alignment, the retrograde trajectory, the close planetary passes, all had natural explanations that did not require invoking extraterrestrial technology. The spectral observations confirmed standard cometary chemistry. The non-gravitational acceleration was consistent with cometary outgassing. The coma structure was consistent with what we see in solar system comets. The weight of evidence pointed overwhelmingly to a natural object. The scientific community's response was measured but clear. The people who actually had access to the data, who analyzed the spectra, who modeled the coma, who measured the light curve, were consistent in their assessment. This was an extraordinary natural comet, not a spacecraft. But here is what the alien hypothesis episode actually demonstrated. Stripped of its entertainment value, it demonstrated the depth of human hunger for significance. The desire to believe that something extraordinary is happening, something intentional, something directed, something that speaks to our place in the cosmos, is one of the most fundamental aspects of human psychology. We are pattern recognition machines. We see faces in clouds and intentions in coincidences. And when something as genuinely extraordinary as an interstellar comet arrives in our solar system, the pattern recognition machine goes into overdrive. The scientifically interesting lesson from this is about the need for better data. If we had in situ measurements of 3I/Atlas, if we had sampled it, imaged its surface, measured its density and internal structure, there would be no ambiguity. No alien hypothesis would survive contact with a mass spectrometer. The frustrating irony is that the very absence of a spacecraft mission to 3I/Atlas kept the alien hypothesis alive in the public imagination far longer than it would have survived otherwise. Data is the antidote to speculation, and we did not have enough of it. So here is the argument I want to leave you with. Not a lament, though some lamentation is appropriate, but an argument. We are, right now, in what future historians of science will probably call the era of interstellar object discovery. The first was found in 2017, the second in 2019, the third in 2025. With Rubin Observatory operational, we will likely find the fourth within the next year or two, and the fifth shortly after. The pace of discovery is accelerating. Each of these objects is irreplaceable. Each carries information that cannot be obtained any other way. Each passes through our solar system in months and departs forever. And the window for intercept, the brief, narrow, technically demanding window during which a spacecraft launched from Earth could catch a visitor from another star, is a window that closes faster than our current preparation allows us to respond. The Solar Oberth Maneuver mission proposed for 2035 is a hope, not a plan. It is a demonstration that the physics is not impossible, that with the right hardware, the right trajectory, and a decade of preparation, humanity could in principle chase 3I/Atlas across tens of billions of miles and eventually catch it. But, in principle, is doing a lot of work in that sentence. The mission requires launch vehicles that are not yet fully operational. It requires thermal protection technology at the extreme edge of what has been demonstrated. It requires a flight time measured in decades, with all the institutional and funding challenges that implies. And it would arrive at its target nearly 60 years after 3I/Atlas passed through the inner solar system, at a distance from our sun so great that the sun itself would be just another star in the sky. The better answer, the answer that actually matches the scale of the opportunity, is to build the interceptor before we need it. To fund a spacecraft that sits in readiness, waiting for the next 3I. To develop the rapid response mission architecture that allows us to go from discovery to launch in weeks rather than years. To invest in the propulsion technology, nuclear electric, nuclear thermal, solar sail with laser assist, that would allow us to match velocities with fast, retrograde interstellar objects rather than merely chasing them in despair. This is not cheap. Nothing in space exploration is cheap. But it is not exorbitantly expensive by the standards of what space agencies already spend. A ready-state interceptor mission, kept in low Earth orbit and maintained by a small dedicated team, would cost a fraction of a major planetary flagship mission. The scientific return, when the opportunity eventually arrives, as it will, would be among the greatest in the history of the science. The decision about whether to build that interceptor will be made not by scientists, but by the political process through which science gets funded in the democratic societies that operate the world's major space agencies. It will be influenced by public opinion, by congressional priorities, by the decisions of agency leadership, by the advocacy of scientific societies, and by the stories that get told about why this matters. Stories like this one. The universe has been extraordinarily patient with us. It has been sending visitors from other solar systems across the unimaginable distances of interstellar space, delivering them to our doorstep at no cost, and it has been doing this for as long as our solar system has existed. We have only been able to detect these visitors for about 8 years, and in those 8 years, 3 of them have come and gone without us ever touching one. The patience of the universe is a reminder that time, on cosmic scales, is essentially infinite. The visitor we missed will be replaced by another one, and another. The interstellar dark is full of ancient travelers, and some number of them will always be transiting our neighborhood. The impatience, the urgency belongs entirely to us, because we are not on cosmic timescales. We are on human timescales, and on human timescales, every interstellar object that passes without a probe is a chapter of cosmic history that closes without being read. 3I/Atlas passed through our solar system in 2025. It will be fully beyond Jupiter's orbit sometime in 2026. It will pass beyond Neptune's orbit in roughly a decade. It will cross the heliopause, the outer boundary of our sun's reach, where the solar wind meets the interstellar medium, perhaps 30 years from now. And then it will be between the stars again. If the 2035 mission launches and uses the solar Oberth maneuver correctly, a probe could catch up with 3I/Atlas somewhere around 2070, at the edge of the inner Oort cloud, in the deepest, coldest, darkest part of our sun's gravitational domain. It would fly past in minutes. It would photograph the nucleus. It would measure the composition of what remains of the coma, whatever thin whisper of outgassing activity might still be detectable at that distance. And it would send that data back at the speed of light across 732 astronomical units of space, taking about 4 days to arrive at Earth. The engineers who design that mission today may not live to see its science return. The scientists who advocate for it now may have retired or died by the time the data arrives. This is a sacrifice that the history of science has always required of people who care about knowledge more than credit. The designers of Voyager are now in their 70s and 80s. The scientists who proposed Cassini's mission to Saturn did not all live to see the grand finale in 2017. The vision required for transformative science often outlives the individuals who hold it. But the vision persists. The knowledge accumulates, the capability grows, and the universe keeps sending us things to look at. 3I/Atlas, already receding into the outer darkness, doesn't know it changed something. Doesn't know that the papers it generated, the debates it sparked, the public attention it drew, the frustration it created, all of this may ultimately result in a different posture toward the next interstellar visitor. Doesn't know that for a few months in 2025, it was the most watched, most debated, most scientifically scrutinized object in the sky, and that its passage fundamentally altered the conversation about humanity's readiness to explore beyond our solar system. It doesn't know, but we know, and knowing is at least a beginning. The question, as always, is what we do with what we know. The universe has given us the question. The answer is ours to write, not in equations on a blackboard, but in steel and copper and carbon fiber and rocket fuel, in congressional appropriations and launch manifests and the patient, unglamorous work of people who build things that will fly through space long after their builders are gone. The next interstellar object is out there. It is moving. It is old. It carries information we cannot read from here, and it will arrive on its own schedule with no regard whatsoever for whether we are ready. I hope we are. And I want to be specific about what ready means, because in the context of interstellar object intercept missions, readiness is not an abstract aspiration. It is an engineering specification. It is a budget line item. It is a roster of people who show up to work every day at a facility that exists. Let me paint the picture of what readiness would actually look like, because I think the concreteness of it matters. Readiness means a spacecraft, let's call it the Interstellar Object Interceptor or IOI, that is assembled, tested, and stored in a state of launch readiness. Not a blueprint. Not a phase study. A physical spacecraft approximately the mass and size of New Horizons, with instruments selected for rapid characterization of an unknown cometary body. A high-resolution camera, a dust analyzer, a mass spectrometer for the gas-phase coma environment, a magnetometer, a near-infrared spectrograph. All of these technologies exist today. They have all flown on previous missions. There is no exotic technology required. The spacecraft itself is not the hard part. The hard part is the propulsion. To intercept an interstellar object that may be moving retrograde at 60 or more kilometers per second relative to Earth requires delta-v that exceeds what a single conventional launch vehicle can deliver. But there are options, and they become more viable every year. Nuclear thermal propulsion, engines that heat a propellant using a nuclear reactor rather than chemical combustion, can achieve specific impulse roughly twice that of the best chemical engines. This means, for the same mass of propellant, you get twice the velocity change. With nuclear thermal propulsion, missions that are impossible with chemical engines become merely difficult. And merely difficult is a description that the space exploration community has consistently been able to overcome when sufficiently motivated. The political infrastructure of readiness means a dedicated line in the NASA budget or ESAs or a coalition of space agencies that funds the maintenance of the IOI spacecraft and a small operations team, regardless of whether an interstellar object has been detected. This is the hardest part, not technically, politically, because funding a mission with no specific launch date is uncomfortable for congressional appropriators who want to show constituents specific outcomes for specific investments. It requires making the case that the investment is in readiness, in capability, in the option value of being able to respond, and that this option value is worth paying for even in years when no interstellar object appears. This is not unprecedented. The United States maintains strategic petroleum reserves not because it expects an oil embargo every year, but because having the reserve is valuable insurance. Militaries maintain readiness capabilities that they hope never to use. The argument for a standing interstellar object interceptor is fundamentally an argument about insurance, about the value of being ready for an opportunity that will definitely come, but whose timing cannot be predicted. The scientific community, to its credit, has been making this argument more forcefully in the wake of 3I/Atlas than at any previous point. The mission concept studies are being written. The advocacy is being organized. The lesson of 3I/Atlas has not been wasted. Whether it will be sufficient to change the budgetary reality, that is a different question. One that depends on factors beyond the control of scientists. But it is a question that deserves to be answered correctly, because the cost of getting it wrong is not just a missed scientific opportunity. It is a missed chapter of cosmic history. And unlike missed conference papers or delayed experiments, missed cosmic history is not recoverable. You cannot schedule a new visit from 3I/Atlas. It will not come back. The universe does not offer refunds. It does not reschedule visits. It sends what it sends, when it sends it, on trajectories determined by gravitational physics that operated billions of years before we existed and will continue to operate billions of years after we are gone. What we can control is whether we are there to meet it. 3I/Atlas has now joined Oumuamua and Borisov as the three known interstellar visitors to our solar system. 3 objects from beyond our star. 3 ancient travelers from distant solar systems, glimpsed briefly by human instruments and then released back into the interstellar dark. 3 opportunities studied through telescopes, analyzed in papers, debated at conferences, and ultimately watched departing without a single human-made object ever coming close to them. The 4th will come. The mathematics of the interstellar flux, the rate at which interstellar objects pass through a volume of space the size of our solar system, suggests that with Rubin Observatory watching, we will find the next one soon. Perhaps within a year, perhaps already by the time you are reading or hearing these words. When it does come, the scientists will scramble again. The telescopes will be pointed. The papers will flow. The measurements will be made. The debates will be had. And the fundamental question will be the same one it has been since Oumuamua. Do we have a probe ready to go? I do not know what the answer to that question will be when the 4th interstellar object is announced. I know what the answer should be. I know what the answer has been for every interstellar object we have discovered so far. And I know what kind of civilization I want us to be. Not a civilization that watches the universe go by from a safe distance, recording what it sees with beautiful instruments and filing the observations in well-organized databases, but a civilization that reaches out, that touches the things it finds interesting, that refuses to accept that the gap between seeing and knowing is unbridgeable. That is the civilization that built Apollo, that built Voyager, that sent New Horizons on a 9-year journey to photograph a world at the edge of our solar system that most people had never thought about, that landed Curiosity on Mars and Perseverance and deployed a helicopter on another planet, that put a spacecraft in orbit around the asteroid Bennu and brought back a sample of it to Earth. These were not easy things. None of them were guaranteed to succeed. All of them required sustained commitment over timescales that exceeded the attention span of news cycles and political terms. And every single one of them expanded what it means to be human in ways that are genuinely difficult to measure but impossible to deny. An interstellar object interceptor mission would be harder than any of those. It would require faster development, more capable propulsion, longer flight times, and patience measured in decades rather than years. It would push the limits of thermal engineering, of deep space communication, of autonomous spacecraft operation at distances where round-trip communication times stretch into days. And it would bring back data that is, in the deepest sense, irreplaceable. I have been asked more than once whether it is worth devoting the resources and attention of a civilization to questions like this. Whether the mysteries of interstellar comets, or the composition of another solar system's planetary building blocks, deserve priority alongside the more pressing challenges of life here on Earth. It is a fair question. It deserves a serious answer. Here is mine. Science does not compete with human welfare. It is one of the foundations of it. The technologies that keep people warm, fed, healthy, and connected are built on the foundations of basic research that was pursued not for immediate practical application, but for the satisfaction of understanding how the universe works. The lasers in fiber optic cables were developed by physicists studying quantum mechanics. The GPS satellites that navigate our cars depend on corrections derived from general relativity. The material science that makes modern medicine possible was built on crystallography and quantum chemistry. Understanding the universe is not a luxury. It is one of the things we do that makes us what we are, and it has a habit of paying dividends in ways that were entirely unforeseeable at the time the research was conducted. And beyond the practical argument, there is a simpler one. We are the only species on this planet, possibly in this galaxy, possibly in the observable universe, that looks up at the night sky and asks, "What is that?" and then builds machines to go find out. That capacity, that curiosity, that insistence on knowing rather than just seeing. It is the most extraordinary thing about us. It is what makes us worth saving. 3I/Atlas reminded us of what we don't yet know, of how far we still are from being able to answer the most fundamental questions about our place in the cosmos, of the gap between our ability to detect and our ability to explore. But it also reminded us of what we have already built: the telescopes, the instruments, the global networks of observation, the mathematical and computational infrastructure that allows a rock from another solar system to be characterized in weeks rather than decades. That is genuinely extraordinary. That is worth celebrating, even as we honestly confront what remains beyond our reach. The next interstellar visitor will come, and the conversation it starts about readiness, about ambition, about what kind of civilization we choose to be, that conversation has already begun. 3I/Atlas started it. Whether we have the wisdom and the will to answer it correctly, that is the only question that matters now.